Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The solar system is often imagined in a family of rocky planets circling close to the sun and giant gas worlds drifting farther out. But this familiar picture hides one of its most fascinating realities. Beyond the warm inner regions lies a realm dominated by ice, darkness, and cold. A vast domain where water behaves in unfamiliar ways and entire worlds are shaped by frozen materials. These are the ice worlds and ocean worlds of the solar system, places where ice is not merely a surface feature, but a defining element of geology, chemistry, and potential habitability. Understanding these worlds reshapes our ideas about where life might exist and how planetary systems evolve. Ice in the solar system is far more diverse than the ice we encounter on Earth. On our planet, ice is almost always frozen water, forming glaciers, snow, and sea ice. In the outer solar system, ice can be water, but it can also be frozen carbon dioxide, methane, ammonia, nitrogen, and many other compounds. These materials freeze at different temperatures and pressures, meaning that a world considered icy might be dominated by substances that behave nothing like terrestrial ice. On some moons, water ice is as hard as rock, forming towering mountains and deep canyons. On others, it may be warm and soft beneath the surface, slowly flowing like thick honey over geological timescales. The ice worlds of the solar system begin just beyond the asteroid belt, where temperatures are low enough for volatile compounds to freeze and remain stable for billions of years. Jupiter's system marks the transition into this icy realm. While Jupiter itself is a gas giant, its large moons reveal a spectrum of icy environments. Europa, Ganymede, and Callisto are dominated by water ice, each telling a different story about internal heat, geological activity, and the possible presence of subsurface oceans. These moons are not static frozen balls, but dynamic worlds shaped by tidal forces, radioactive heating, and complex chemistry. Europa stands out as one of the most intriguing objects in the solar system. Slightly smaller than Earth's moon, Europa is covered by a bright, cracked shell of water ice. Its surface is crisscrossed by dark lines and ridges, evidence that the ice has fractured, shifted, and refrozen countless times. Beneath this icy crust lies a global ocean of liquid water, kept warm by tidal heating as Europa is flexed by Jupiter's immense gravity. This ocean may contain more water than all of Earth's oceans combined, making Europa one of the most water-rich environments known. What makes Europa especially compelling is the possibility that its ocean is in contact with a rocky seafloor. On Earth, life thrives in deep ocean environments where sunlight never reaches, fueled instead by chemical energy from hydrothermal vents. If similar processes occur on Europa, they could provide the ingredients needed for life: liquid water, chemical energy, and essential elements. The ice shell above acts as both a barrier and a window, isolating the ocean while occasionally allowing material to exchange with the surface through cracks and plumes. Ganymede, Jupiter's largest moon and the largest moon in the solar system, presents a different kind of ice world. Larger than the planet Mercury, Ganymede has a complex internal structure with multiple layers of ice and possibly several subsurface oceans stacked between them. Unlike Europa, Ganymede has its own magnetic field, suggesting a dynamic interior. Its surface shows regions of ancient dark terrain and younger, brighter grooved terrain, indicating a long history of geological activity driven by internal processes. Callisto, by contrast, appears more ancient and less active. Its heavily cratered surface suggests that it has changed little for billions of years. Yet even Callisto may harbor a subsurface ocean beneath its thick ice shell. This challenges the idea that geological activity is required for liquid water to exist, showing instead that internal heat from radioactive decay and insulation by ice can be enough to preserve oceans over immense timescales. Moving outward, Saturn's system introduces a new set of icy worlds, each with unique characteristics. Titan, Saturn's largest moon, is often described as one of the most Earth-like bodies in the solar system, not because it is warm or habitable on the surface, But because it possesses a thick atmosphere, active weather, and stable bodies of liquid on its surface. On Titan, however, the liquids are not water but methane and ethane, forming lakes, seas, rivers, and rain under frigid conditions. Titan's surface temperature is so low that water ice behaves like rock, forming mountains and crustal plates, while hydrocarbons take the role of water in shaping landscapes. Beneath this alien surface likely lies a subsurface ocean of water mixed with ammonia, kept liquid by internal heat. This combination of surface chemistry and internal water makes Titan a compelling laboratory for studying prebiotic chemistry, the kinds of chemical processes that may lead to life. Enceladus, another moon of Saturn, is much smaller than Titan, but arguably even more astonishing. This tiny ice world is intensely active, with geysers of water vapor and ice particles erupting from fractures near its south pole. These plumes feed Saturn's E-ring and to provide direct evidence of a subsurface ocean beneath Enceladus's icy crust. The plumes contain water, salts, organic molecules, and even hydrogen, indicating chemical reactions between water and rock occurring deep below the surface. The discovery of Enceladus transformed our understanding of habitability. Here was a small, cold moon, far from the sun, yet possessing liquid water, energy sources, and organic chemistry. The fact that material from its ocean is naturally ejected into space makes Enceladus one of the most accessible places to search for signs of life beyond Earth, without the need to drill through kilometers of ice. Beyond Saturn lies Uranus, a planet often overlooked but surrounded by a fascinating system of icy moons. Uranus itself is classified as an ice giant, composed largely of water, ammonia, and methane ices under extreme pressure. Its moons, such as Miranda, Ariel, Umbriel, Titania, and Oberon, are mixtures of rock and ice, showing evidence of past geological activity. Miranda in particular displays bizarre terrain with towering cliffs, patchwork regions, and signs of intense deformation, suggesting a turbulent history despite its small size. Neptune, the outermost giant planet, hosts Triton, one of the coldest known worlds in the solar system. Triton is unique among large moons because it orbits Neptune in a retrograde direction, indicating that it was likely captured from the Kuiper Belt. Its surface is covered with nitrogen ice, methane ice, and water ice, sculpted into plains, ridges, and geyser-like features that erupt nitrogen gas. Triton's activity suggests that even at extreme distances from the sun, internal heat can drive geological processes. The Kuiper Belt itself is a vast reservoir of icy worlds beyond Neptune, extending tens of billions of kilometers into space. It contains countless objects ranging from small icy bodies to dwarf planets like Pluto, Eris, Haumea, and Makemake. These worlds preserve some of the most ancient material from the early solar system, offering a window into planetary formation processes. Pluto, once considered the ninth planet, is now recognized as one of the most complex ice worlds ever explored. Data from the New Horizons mission revealed a surprisingly active world with mountains of water ice, vast plains of nitrogen ice, glaciers flowing across the surface, and possible subsurface oceans. Pluto's heart-shaped region, Sputnik Planitia, is a basin filled with nitrogen, carbon monoxide, and methane ice that appears to be constantly renewed by convection. Despite its small size and distance from the sun, Pluto demonstrates that icy worlds can remain geologically active for billions of years. Ocean worlds represent a special category within the broader class of ice worlds. These are bodies that possess or are strongly suspected to possess liquid water oceans beneath their icy shells. In addition to Europa, Enceladus, Titan, Ganymede, and possibly Callisto and Pluto, other candidates include moons like Dione, Rhea, and even some large Kuiper Belt objects. The realization that oceans may be common in the solar system has fundamentally changed our perspective on where life might arise. On Earth, liquid water is intimately tied to life as we know it. The presence of subsurface oceans on multiple worlds suggests that habitable environments may exist far from the traditional habitable zone around a star. Instead of relying on sunlight, these environments may be powered by internal heat, tidal forces, and chemical energy. This expands the concept of habitability from a narrow ring around stars to potentially countless hidden oceans throughout planetary systems. The physics that allow ocean worlds to exist are both subtle and powerful. Ice acts as an insulating blanket, trapping heat within a planet or moon. Tidal heating caused by gravitational interactions with a parent planet and neighboring moons can flex a moon's interior, generating heat through friction. Radioactive decay within rocky cores provides an additional long-term heat source. Together, these processes can keep water liquid beneath kilometers of ice for billions of years. The chemistry of these hidden oceans is equally important. Interactions between water and rock can produce hydrogen and other compounds that serve as energy sources for life. Salts dissolved in the water lower its freezing point, making it easier for oceans to persist. Organic molecules, either delivered by comets or produced through internal processes, add further complexity. In some cases, materials from the ocean can reach the surface, as seen on Enceladus and possibly Europa, offering clues to what lies below. Ice worlds also play a crucial role in the broader story of the solar system. They are relics of the outer protoplanetary disk, where temperatures were low and volatile materials could condense. Studying their compositions helps scientists understand how planets formed and how materials were distributed during the early stages of solar system history. Ice-rich bodies may have delivered water and organic compounds to the inner planets, including Earth, influencing the emergence of life. The exploration of ice worlds has accelerated dramatically in recent decades. Spacecraft missions have transformed points of light into richly detailed worlds. Flybys, orbiters, and landers have revealed active geology, complex chemistry, and environments that challenge traditional assumptions. Future missions aim to go even further, probing beneath the ice, sampling plumes, and searching directly for signs of life. The search for life on ice and ocean worlds is not driven by optimism alone, but by a growing body of evidence. These worlds meet many of the criteria considered essential for life: liquid water, energy sources, and chemical diversity. While life, if it exists, may be microbial and unfamiliar, its discovery would profoundly alter our understanding of biology and our place in the universe. Even if life is not found, ice worlds remain invaluable for understanding planetary processes. They demonstrate how planets and moons evolve under extreme conditions, how geology can operate without sunlight, and how complex systems emerge from simple ingredients. They also serve as analogs for icy exoplanets and moons that may be common throughout the galaxy. As we look beyond our solar system, the lessons learned from ice worlds and ocean worlds become even more significant. Many exoplanets detected so far are thought to be water-rich or ice-rich, and some may host subsurface oceans similar to those found closer to home. By studying the icy realms of our own solar system, we develop the tools and concepts needed to interpret distant worlds orbiting other stars. The solar system's ice worlds and ocean worlds remind us that warmth and life are not confined to places bathed in sunlight. In the cold and darkness, beneath thick shells of ice, entire oceans may exist, quietly enduring for billions of years. These hidden seas expand the boundaries of habitability and challenge us to rethink what it means for a world to be alive with possibility. They show that even in the most unlikely places, nature finds ways to create complexity, motion, and perhaps even life itself. Beyond the worlds already explored, the idea of ice worlds and ocean worlds continues to grow richer as scientists reconsider bodies once thought to be simple and inert. Even small moons and distant dwarf planets may conceal hidden oceans or layers of partially melted ice. These environments challenge the traditional view that size and proximity to the sun determine geological activity. Instead, they reveal that heat, chemistry, and time can combine in unexpected ways to create long-lived, dynamic systems beneath frozen surfaces. One of the most important concepts in understanding ice worlds is the behavior of water under extreme pressure. On Earth, water freezes into familiar forms of ice, but in the interiors of large icy moons, pressure can transform water ice into exotic crystalline phases that do not exist naturally on the surface of our planet. These high-pressure ices can form dense layers beneath subsurface oceans, acting as barriers between liquid water and rocky interiors. In some worlds, however, the ocean may lie directly atop rock, enabling chemical reactions essential for habitability. The exact arrangement of these layers depends on a moon's size, composition, and thermal history, making each ice world unique. Tidal forces play a central role in shaping ocean worlds, particularly those orbiting giant planets. As a moon follows an elliptical orbit, gravitational pull varies, stretching and compressing its interior. This constant flexing generates heat through friction, a process known as tidal heating. Europa and Enceladus are prime examples of worlds where tidal heating maintains liquid oceans despite surface temperatures far below the freezing point of water. Without this energy source, these oceans would have frozen solid long ago. Tidal interactions also influence surface geology, creating fractures, ridges, and in some cases, dramatic eruptions that transport material from the interior into space. The surfaces of ice worlds often preserve a record of internal processes in the form of patterns, colors, and structures. On Europa, the network of dark lines reflects repeated cycles of cracking and refreezing, possibly driven by oceanic movement below. On Enceladus, the south polar terrain is scarred by deep fractures known as tiger stripes, from which plumes continuously erupt. Pluto's nitrogen glaciers reveal convection cells that slowly churn the ice, erasing impact craters and renewing the surface. These features show that ice, under the right conditions, can be as geologically active as molten rock. Ocean worlds also raise profound questions about the limits of life. On Earth, life has adapted to extreme environments, such as deep-sea hydrothermal vents, subglacial lakes, and highly saline waters. These ecosystems demonstrate that sunlight is not a requirement for life, as long as chemical energy and liquid water are present. In subsurface oceans, life would likely rely on chemical reactions between water and minerals, drawing energy from redox gradients and geothermal activity. While such life might be simple, its existence would confirm that biology is not unique to Earth. The study of ice worlds also intersects with the origin of Earth's own oceans. Many scientists believe that water was delivered to the early Earth by icy bodies from the outer solar system, such as comets and water-rich asteroids. By examining the composition of ice worlds and Kuiper Belt objects, researchers can better understand the sources of Earth's water and organic materials. This connection links the frozen outskirts of the solar system to the emergence of life on a warm, rocky planet. Ice giants like Uranus and Neptune occupy a middle ground between gas giants and solid ice worlds. Their interiors are dominated by hot, dense fluids composed of water, ammonia, and methane under extreme pressure. Although they lack solid surfaces, these planets are essential to understanding ice-rich environments on a planetary scale. Their unusual magnetic fields, which are tilted and offset from their centers, hint at complex internal dynamics that differ fundamentally from those of Jupiter and Saturn. Studying these planets helps scientists interpret the many Neptune-sized exoplanets discovered around other stars. The concept of ocean worlds extends beyond moons to include some dwarf planets and large trans-Neptunian objects. Pluto, with its layered ice shell and possible subsurface ocean, demonstrates that even small bodies can retain heat for billions of years. Other Kuiper Belt objects may share similar characteristics, especially those with thick, insulating ice layers in the presence of antifreeze compounds like ammonia. These discoveries suggest that hidden oceans may be widespread in the outer solar system, vastly increasing the number of potentially habitable environments. Future exploration of ice worlds aims to move beyond observation toward direct investigation of subsurface environments. Proposed missions include orbiters equipped with ice-penetrating radar, landers capable of analyzing surface material, and even concepts for cryobots that could melt through ice shells to reach underlying oceans. Sampling plumes, as already done at Enceladus, offers a promising approach to studying ocean chemistry without the immense technical challenges of drilling through ice. The technological challenges of exploring ice worlds are immense, but so are the rewards. Instruments must survive extreme cold, intense radiation, and long communication delays. Yet each mission brings new insights into planetary processes and the potential for life. The exploration of these distant worlds represents a natural extension of humanity's desire to understand its origins and its place in the universe. Ice worlds also serve as powerful reminders that planetary systems are shaped by both universal laws and unique circumstances. The same physics governs all planets, yet small differences in orbit, composition, and history can lead to radically different outcomes. A moon slightly closer to its planet may experience intense tidal heating and become an ocean world, while a similar moon farther away remains frozen and inert. These delicate balances highlight the complexity and diversity of planetary evolution. As astronomical techniques improve, the study of ice worlds in our solar system informs the search for similar environments around other stars. Many exoplanets discovered to date are likely water-rich or ice-dominated, and some may host subsurface oceans beneath thick ice layers. By understanding how ice worlds function close to home, scientists can better interpret distant signals and refine their search for habitable environments beyond the solar system. The idea that oceans can exist in perpetual darkness beneath kilometers of ice challenges our intuitive notions of what a life-supporting world looks like. It suggests that the universe may be filled with hidden habitats, isolated yet stable, waiting to be discovered. Even if life is rare, the sheer number of potential ocean worlds increases the odds that biology has emerged elsewhere. In the end, the ice worlds and ocean worlds of the solar system reveal a universe far more dynamic and surprising than once imagined. They show that heat can be generated without sunlight, that ice can flow and fracture like rock, and that oceans can persist in the coldest regions of space. These worlds blur the line between the living and the lifeless, inviting us to explore further and question long-held assumptions. As exploration continues, ice worlds will remain at the forefront of planetary science and astrobiology. They are not merely frozen remnants of planetary formation, but active, evolving systems with the potential to reshape our understanding of life itself. In their silent, hidden oceans, they may hold answers to one of humanity's oldest questions. Are we alone, or is life a natural consequence of the universe, wherever the conditions allow it to begin? Another crucial aspect of ice worlds and ocean worlds is time. These environments are not brief or temporary phases in planetary evolution, but can persist for billions of years. The insulating properties of thick ice shells allow internal heat to escape very slowly, meaning that subsurface oceans may survive long after surface conditions become hostile. This longevity is important for any potential life, as it provides the extended stability needed for complex chemistry and biological processes to develop. On Earth, life emerged relatively quickly once conditions allowed, but it had also required long periods of environmental stability to diversify and evolve. Subsurface oceans, shielded from asteroid impacts, radiation, and extreme climate swings, may offer even more stable environments than Earth's surface. In this sense, ice-covered oceans could be among the safest habitats for life in a volatile universe. The ice acts as a protective lid, preserving liquid water and shielding it from cosmic hazards. The darkness of these oceans, however, imposes strict limits on the kinds of ecosystems that could exist. Without sunlight, photosynthesis as we know it would be impossible. Instead, life would depend on chemosynthesis, drawing energy from chemical reactions involving hydrogen, sulfur, iron, or other compounds released through interactions between water and rock. On Earth, such ecosystems exist near hydrothermal vents and beneath thick ice sheets, demonstrating that life can flourish without light. The presence or absence of a rocky seafloor is therefore a key factor in evaluating the habitability of an ocean world. Direct contact between liquid water and silicate rock enables a wide range of chemical reactions that supply nutrients and energy. Worlds like Europa and Enceladus are thought to have this contact, increasing their astrobiological potential. In contrast, ocean layers separated from rock by thick, high-pressure ice may be more chemically limited, though not necessarily sterile. Ice worlds also display a remarkable diversity of surface colors and textures, reflecting variations in composition and radiation processing. Icy surfaces exposed to charged particles and ultraviolet radiation can develop complex organic compounds known as tholins, which give Titan and Pluto their reddish hues. These materials are chemically rich and may resemble some of the organic substances that played a role in the origin of life on Earth. Their presence demonstrates that complex chemistry can occur even in the coldest regions of the solar system. Seasonal cycles, though subtle, can also shape ice worlds. On Pluto, for example, its elongated orbit causes dramatic changes in temperature over long periods, driving the migration of nitrogen and methane ice across the surface. These seasonal processes can reshape landscapes and influence atmospheric pressure, creating a dynamic interplay between surface, atmosphere, and interior. Even in environments far from the sun, change is constant, though it unfolds on timescales much longer than those on Earth. The role of impacts in shaping ice worlds should not be overlooked. While thick ice can erase smaller craters over time, large impacts may fracture ice shells, locally thin them, or even trigger episodes of enhanced geological activity. In some cases, impacts could create temporary melt zones or facilitate exchanges between surface material and subsurface oceans. Such events might introduce new chemical ingredients into hidden oceans, potentially influencing their evolution. Ice worlds also help scientists test models of planetary differentiation, the process by which bodies separate into layers of different composition and density. Many icy moons consist of mixtures of rock and ice that have partially separated into cores, mantles, and shells. Understanding how and when this differentiation occurred provides clues about their formation conditions and thermal histories. These insights, in turn, inform broader theories of how planetary systems assemble and evolve. From a human perspective, ice worlds capture the imagination because they combine familiarity and alienness. Water, ice, and oceans are deeply connected to our own experience. Yet on these worlds, they behave in strange and unexpected ways. Oceans hidden beneath ice, lakes of liquid methane, glaciers of nitrogen, and geysers erupting into vacuum challenge our intuition and expand our sense of what a world can be. The exploration of ice worlds also raises ethical and philosophical questions. If life exists beneath the ice of another world, how should humanity approach its discovery? Protecting potentially living ecosystems from contamination is a major concern in planetary exploration. Space agencies design missions with strict planetary protection protocols to minimize the risk of introducing Earth microbes into pristine environments. These considerations highlight the responsibility that comes with exploration. Looking ahead, ice worlds are likely to remain central targets for planetary science missions. Advances in robotics, material science, and energy systems may one day make it possible to explore subsurface oceans directly. Even before that, improved instruments will allow scientists to analyze surface chemistry, detect subtle gravitational signals of internal oceans, and sample plume material in unprecedented detail. Each step brings us closer to answering fundamental questions about habitability. Ice worlds also serve as natural laboratories for studying climate processes in extreme conditions. By examining how volatile substances cycle between solid, liquid, and gas phases on these worlds, scientists gain insights into atmospheric evolution, surface-atmosphere interactions, and long-term climate stability. These lessons are valuable not only for understanding distant worlds, but also for refining models of Earth's own climate system. In a broader cosmic context, the abundance of ice worlds suggests that water-rich environments may be common throughout the galaxy. Planet formation models indicate that icy materials are plentiful in protoplanetary disks, making it likely that many planetary systems contain ice-rich planets and moons. If subsurface oceans are a natural consequence of these conditions, then the universe may host vast numbers of hidden seas, each a potential cradle for life. The idea that life might exist in places completely isolated from starlight reshapes our understanding of biology. It implies that life could emerge wherever liquid water and energy coexist, even in environments once considered utterly inhospitable. This perspective transforms the search for life from a narrow quest focused on Earth-like planets into a much broader exploration of diverse worlds. Ultimately, the ice worlds and ocean worlds of the solar system remind us that discovery often lies in the unexpected. What were once dismissed as frozen, lifeless remnants have become some of the most exciting and promising objects in planetary science. They challenge our assumptions, inspire new questions, and encourage us to look beneath the surface, both literally and figuratively. As we continue to explore these distant realms, we are likely to uncover surprises that further expand our understanding of planets, oceans, and life itself. Whether or not life is found, ice worlds will remain central to the story of the solar system, revealing how complexity and potential can arise even in the coldest, darkest corners of space. Another dimension that makes ice worlds and ocean worlds so compelling is their role as bridges between planetary science and chemistry. In these environments, physical processes such as freezing, melting, fracturing, and convection interact continuously with chemical reactions. Ice is not inert. It traps gases, concentrates salts, and preserves organic molecules for immense spans of time. As ice warms, cracks, or recrystallizes, it can release these materials, creating localized chemical hotspots that may drive further complexity. This constant interplay between physics and chemistry creates environments that are dynamic rather than static, even when surface temperatures remain extremely low. Radiation plays a subtle but important role on many ice worlds, particularly those orbiting within the intense magnetic fields of giant planets. Energetic particles can penetrate surface ice, breaking molecules apart and forming new compounds through a process known as radiolysis. On Europa, radiation-driven chemistry may produce oxidants on the surface that are later transported into the subsurface ocean through cracks or melting ice. If this exchange occurs efficiently, it could provide an energy source similar to oxygen on Earth, potentially supporting more complex chemical cycles beneath the ice. The thickness of an ice shell strongly influences how an ocean world behaves. Thin ice shells allow more frequent interaction between the surface and the ocean below, increasing the chances that chemical materials can circulate. Thicker shells provide greater insulation but may limit exchange, isolating the ocean more completely. Determining ice thickness is therefore a major focus of planetary science. Using techniques such as gravity measurements, magnetic field analysis, and ice-penetrating radar, each method offers indirect clues about what lies beneath the surface. Ice worlds also force scientists to reconsider the definition of geological activity. Traditionally, geology is associated with molten rock, volcanoes, and tectonic plates. On ice worlds, similar processes occur using frozen materials instead of silicate rock. Cryovolcanism, for example, involves the eruption of water, ammonia, or methane instead of lava. These eruptions can resurface large areas, build ice mountains, and release gases into space or into tenuous atmospheres. Cryovolcanism has been proposed or observed on worlds such as Enceladus, Titan, Triton, and Pluto, highlighting how active ice can be under the right conditions. Atmospheres on ice worlds vary widely, from the thick, nitrogen-rich envelope of Titan to the thin, transient atmospheres of Pluto and Triton. These atmospheres are often closely linked to surface ice, forming through sublimation as ices warm and collapsing back onto the surface as temperatures drop. This ongoing exchange creates seasonal and long-term cycles that shape both the atmosphere and the surface. In some cases, atmospheric chemistry driven by sunlight and radiation produces complex organic molecules that eventually settle onto the surface, enriching the icy crust. The study of ice worlds also benefits from comparisons with Earth's polar regions and subglacial environments. Beneath Antarctica's ice sheets lie liquid lakes and interconnected water systems isolated from the surface for millions of years. Microbial life has been detected in some of these extreme environments, demonstrating that life can persist in cold, dark, high-pressure conditions with limited nutrients. These terrestrial analogs provide valuable insights into how life might survive in subsurface oceans elsewhere, while also highlighting important differences in chemistry and energy availability. Ice worlds challenge not only scientific understanding, but also engineering ingenuity. Designing spacecraft to operate in environments where temperatures can drop below -200 degrees Celsius requires specialized materials and power systems. Solar energy becomes ineffective far from the sun, necessitating alternative power sources capable of functioning reliably for decades. Instruments must be shielded from radiation, protected from contamination, and capable of performing sensitive measurements under harsh conditions. Each successful mission represents a triumph of both science and technology. Beyond their scientific value, ice worlds hold deep philosophical significance. They confront humanity with the possibility that life does not require Earth-like conditions or even surface environments. If life exists beneath the ice of Europa or Enceladus, it would suggest that biology emerges wherever conditions permit, regardless of sunlight or familiar landscapes. This realization would profoundly affect how we view life in the universe, transforming it from a rare anomaly into a potentially common outcome of planetary evolution. Even in the absence of life, ice worlds reveal the remarkable creativity of nature. They show how simple ingredients such as water, rock, and energy can produce a vast range of outcomes, from frozen deserts to hidden oceans and active geysers. They demonstrate that planetary systems are not static collections of objects, but living systems in constant motion, shaped by gravity, heat, and time. The future of ice world exploration promises to deepen these insights further. New missions will refine our understanding of ocean composition, ice dynamics, and internal structure. Advances in data analysis and laboratory experiments will allow scientists to better interpret remote measurements and simulate conditions deep beneath icy shells. Each discovery will feed back into broader theories of planet formation, habitability, and the potential distribution of life in the universe. As our knowledge grows, ice worlds may also influence how humanity thinks about long-term survival and exploration. Subsurface oceans protected by thick ice offer natural shielding from radiation and impacts, suggesting that similar environments could one day serve as refuges for future exploration or even habitation, albeit far beyond current technological capabilities. While such ideas remain speculative, they underscore the broader relevance of studying these distant worlds. In the grand narrative of the solar system, ice worlds and ocean worlds occupy a central and transformative role. They connect the cold outer regions to the warm inner planets through shared materials and histories. They preserve ancient records of planetary formation while actively evolving in the present. Most importantly, they expand the boundaries of where life might exist, inviting us to look beyond familiar horizons. As exploration continues, these frozen worlds will remain among the most compelling targets in space science. They remind us that beneath surfaces that appear lifeless and unchanging, complexity and motion can thrive. In the silent darkness beneath kilometers of ice, entire oceans may endure, shaped by forces both subtle and immense. Whether or not life swims in those hidden seas, their existence alone reshapes our understanding of planets, oceans, and the extraordinary diversity of worlds that orbit our sun. In many ways, ice worlds represent a quiet revolution in planetary science. For much of human history, oceans were assumed to belong only to warm, sunlit planets like Earth. The discovery that oceans can exist beneath thick shells of ice, far from the sun's warmth, has transformed how scientists think about planetary environments. It suggests that liquid water is not an exception, but a recurring outcome when certain physical conditions are met. This realization forces a reassessment of how common habitable environments might be, not only in our solar system, but throughout the galaxy. Ice worlds also highlight the importance of internal energy over external energy. While sunlight dominates Earth's climate and ecosystems, subsurface oceans depend primarily on heat generated from within. Tidal interactions, radioactive decay, and residual heat from formation work together to maintain liquid layers beneath ice. This inward-facing energy system creates environments that are isolated yet persistent, stable over timescales that rival or exceed those of surface oceans on rocky planets. The isolation of subsurface oceans has important implications for evolution. In a sealed environment with limited exchange, biological systems, if they exist, might follow evolutionary paths very different from those on Earth. Without sunlight-driven cycles or frequent environmental disruptions, life could evolve slowly, adapting to narrow ecological niches. Such ecosystems might be simple, yet extraordinarily resilient, surviving unchanged for millions or even billions of years. Alternatively, chemical gradients and localized energy sources could create surprising diversity within these hidden seas. Ice worlds also blur the line between planets and moons in terms of scientific importance. Traditionally, planets were seen as primary targets for the search for life, while moons were considered secondary. The recognition that some moons may be more habitable than many planets has overturned this hierarchy. Europa, Enceladus, and Titan are now regarded as prime targets in astrobiology, sometimes even outranking Mars in their potential to host life today. From a compositional perspective, ice worlds act as archives of the early solar system. Their cold environments preserve volatile compounds that were present during planetary formation. Studying these materials helps scientists reconstruct the chemical inventory of the protoplanetary disk and understand how different regions of the solar system acquired their unique characteristics. In this sense, ice worlds are not only destinations of interest, but also historical records written in ice. The diversity among ice worlds is striking. Some are dominated by water ice, others by nitrogen or methane. Some are geologically active, others appear ancient and quiet. Some possess thick atmospheres, while others are nearly airless. This diversity shows that ice is not a single defining trait, but a versatile component that can lead to many different planetary outcomes. Each ice world is a distinct experiment conducted by nature under slightly different conditions. As technology advances, the possibility of detecting biosignatures in plume material or surface deposits becomes increasingly realistic. Chemical imbalances, unusual organic structures, or isotopic ratios could hint at biological processes occurring beneath the ice. Even ambiguous signals would provide invaluable data, guiding future missions and refining theories about life in extreme environments. The search itself drives innovation, pushing the limits of what spacecraft can detect and endure. Ice worlds also inspire a sense of humility. They remind us that Earth's surface environment, though hospitable and familiar, represents only one of many possible ways a planet or moon can support complexity. Life, if it exists elsewhere, may not resemble terrestrial organisms in appearance or behavior, yet it could share the same fundamental dependence on water and energy. This broader perspective encourages openness and caution in interpreting data, avoiding assumptions rooted too strongly in Earth-based experience. In the cultural imagination, ice worlds often evoke images of desolation and stillness. Science reveals a very different reality, worlds where ice fractures, flows, erupts, and conceals oceans in constant motion. Beneath their frozen exteriors, these worlds may be as dynamic as any volcanic planet, shaped by invisible forces acting over immense timescales. This contrast between appearance and reality is one of the most compelling aspects of their study. Ultimately, the story of ice worlds and ocean worlds is a story about hidden complexity. It teaches that the most interesting processes may occur out of sight, beneath surfaces that appear simple and uniform. It encourages exploration not only outward into space but inward, toward layers and environments that defy easy observation. In doing so, it reshapes our understanding of what a world can be. As humanity continues to explore the solar system, ice worlds will remain symbols of possibility. They stand as reminders that even in the coldest, darkest regions, conditions can exist that nurture motion, chemistry, and perhaps life. Whether future missions confirm the presence of living organisms or not, the discovery of hidden oceans alone has already changed how we see our cosmic neighborhood. In the vast silence beyond the inner planets, ice worlds quietly orbit their parent planets and the sun, preserving oceans beneath frozen shells. They are worlds of patience and endurance, shaped slowly by gravity and heat. By studying them, we learn that the universe is not only stranger than we imagine, but richer in potential. In that realization, ice worlds and ocean worlds take their place as some of the most important and inspiring members of the solar system family.